let's take a look at the geometrical representations. So in particular, first of all, circles. We talked a bit about that before. And there it is, our standard circle, centre at the origin. And we saw that it was z times z conjugate equals r squared. But now we have another way we could write it. We could simply say, oh, hang on, every point on this circle, the modulus of z is equal to some constant number. Its distance from the centre is the same. And if we were to shift that circle, we saw the shift happens in both factors there, so not only z minus w but in the conjugate as well. But for modulus, what we're saying is, hey, the length of any of these when we measure the vector to that point will always be the same. So again, we've got that shift happening, z minus omega. We see something like that then. If we just simply see the modulus equals a constant number, we know, hey, we've got a circle. We know that's a circle. Alright, so let's find out what these circles are. X squared plus y squared equals 16. Well, obviously we know what that is. But if I was to put it in terms of complex numbers, I'd say, oh, well, that's the modulus of z equals 4. If I was to put it in conjugate form, it would be z times z conjugate equals 16. Now this highlights where we've got to be careful. We're so used to saying x squared plus y squared is the radius squared, and when it's in conjugate form, that's fine. But when we're just talking about the modulus, it's not 16, we don't square it. So it's the modulus of z is equal to 4, the actual radius itself. So just be careful for that. Ooh, gonna have to complete the square on this one, and we get, there we go. So we now know where the centre is, we know what the radius is. That would be the modulus of z plus 3 minus 2i is equal to 5. And in conjugate form, we would write it like that. Let's go the other way. Let's find the centre and the radius. Modulus of z minus 5 minus I is equal to 2. We can now read off that because we know it's z minus the centre. So the centre is 5, 1, and we know that is actually the radius. So the radius is 2. Here's one in conjugate form, but again we can just read off it. We know it's z minus the centre, so the centre is minus 4 minus 1, but this one is where it's radius squared. Radius is 7. One like this. Not immediately obvious, that one. That's not in one of those forms. Alright, well if I'm not sure what it is, let's bring it back to Cartesian form and then we can get an idea. First thing I'm going to do is I'm going to factorise out the 3 out of the absolute value. 3 times the absolute value of z is equal to absolute value or magnitude is z plus 2 minus I. Let's replace z with x plus iy, and then the right hand side grouping our real and imaginaries. Looks like it is going to be a circle because the coefficient of the x squared and the y squared is going to end up being the same. Expand the whole thing out, bring it to one side. I prefer to complete the square when it's just x squared rather than 8x squared, so I'll divide everything by 8, and there I have it. So I know the centre, a quarter minus 1/8, radius is 3 root 5 on 8. Don't immediately recognise it, put it in the Cartesian form and then you'll get something that you should be able to recognise. Z times Z conjugate plus 2 times Z plus Z conjugate. Again, don't recognise that. Let's put it in the Cartesian. We know Z conjugate, x squared plus y squared. Z plus Z conjugate, well that's going to be twice the real part, so 2x, but times it by the 2. Here's another circle. There it is. Centre, minus 2, 0, radius 2. Okay, lines. We talked about horizontal lines. Everything on that line would have the same imaginary value. And we talked about vertical lines. Everyone on that one would have the same real value. But what about lines that are oblique, some sort of an angle? I can always find the perpendicular bisector of any 2 points. We know that. And it would end up being a line. Therefore, if you put that into reverse, any line should be able to be the perpendicular bisector of some pair of points. Oh, there's actually an infinite number you could pick, but it should be possible. Why do I get from that? Well, think about that. What we're saying is any point on this line will be the same distance to both of these points. In other words, the modulus when I join z up to one of those points, omega 1, would be equal to the modulus when I join z up to the other point. So if I see something like that, modulus equals modulus, I got a straight line. I know this is going to be a line. I see this. There it is. It's in that form. I know that's a straight line. What is the straight line? Oh, well, I could put it into Cartesian form and let's work it out. Group things together. This time the x squareds and the y squareds will cancel. So yeah, we do get a straight line. There it is. 6x plus 4y plus 3. Of course, the other way I could do it is, well, hang on, I know that line is going to be the perpendicular bisector of those 2 points. So I could use coordinate geometry in a different way. If it's the perpendicular bisector of those 2 points, then I know the midpoint must be on the line. I'll find the midpoint. But I also know the slope joining those 2 points, well, the line I want will be perpendicular to it. So if I find the slope of the line joining those 2 points, 2/3, then the slope I want is going to be -3 on 2. I got a point, I got a slope, I could put it in the point slope formula and we get the answer. There are a couple of ways I could approach that. But the beauty of knowing it's the perpendicular bisector is when you get something like this. They haven't actually asked us to find the equation. All they said is sketch it. So I don't need to waste time. I can go, righto, Z's going to join the points 4i. So I know 4 is important, and -2i. It's going to be the perpendicular bisector of these 2 points. Well, what's in the middle of those 2 points? Well, 1 is. And this makes life a little bit easier because it's a vertical line, therefore the one I'm looking for is a horizontal line. And actually I could find the equation if they had asked me to, because it's such a simple line. But there it is, there's our perpendicular bisector. So the locus that they're looking for. Well, let's move on to rays then. Now, circles and lines we'd seen before, rays. Remember, a ray, well, remember there's 3 things. There's rays, intervals and lines. We don't often talk about rays that much. Intervals are ones that have those definite ending and starting points. Lines are ones that keep going in either direction. It's not bounded. Rays are the ones where it's bounded on one end, but then goes off. So something like this. Every point on this ray would have the same argument. No matter where I pick, it's always going to make the same angle with the horizontal. So that particular thing could be described as the argument of z is equal to theta. But you will notice I have circled the starting point. Starting point is not included because you haven't moved anywhere yet. So the starting point can't have an argument. It's like the number 0. What direction is it? If you were to draw the 0 vector, well, hang on, 0 vector, it's not going anywhere. It hasn't got a direction. So we always circle the starting point. And we could also shift that starting point, and if I had something like that, well, now all we're saying is, hey, the vector z minus w. So when I draw it up to that, we get theta. We're now going to draw a region. I want all the points such that the modulus of z is less than 1 and the argument of z is in between 0 and pi on 4. Well, the first one we know is a circle. The boundary is not included, so I've dotted that. And we know the radius is 1. And we'll be inside that circle because we want all the ones where it's less than 1. The argument. Well, the argument of z is pi on 4, and it's equal to as well, would be going off at 45 degrees or pi on 4. So there's the ray, but circling the starting point. But I've also got the argument of z is equal to 0, which would be going to the right. We want the ones that are in between these two, but inside the circle as well. So we're in there, but there's a couple more things I need to do here to complete it. I've got a boundary here which is not included. Therefore the point of intersection is not included. I'll circle those points of intersection. And there's another thing I should do as well, because outside this circle is not included. Those lines should be dotted after the circle because they're not included as well. That's the region we're looking for. We're going to sketch this. So we look at it and we say, what is it? Modulus of z plus some other number in this case is equal to 2. It's a circle. We recognise that's a circle. Let's draw it. The centre is going to be at -2, 2. The radius is 2. This is where you need to be careful with your diagrams, because this one, the axes end up being tangents. So you don't want to just draw a rough circle and all of a sudden it overlaps the axis or something like that. I mean, they're tangents, so we make sure it's in the correct position. What are all the possible values for the argument of z? So if we were to pick any point on this circle, how would their arguments vary between what and what? And that's where it's kind of nice that the coordinate axes there are the tangents, because we're joining it up to the origin, the vectors, and we want to know, well, what's the minimum and the maximum? So when I draw in those tangents, which happen to be the coordinate axes in this case, so we know all our arguments are going between pi on 2 and pi. They're all the possibilities. What about if they asked for the modulus? So again, if we were to join up any point on the circle to the origin, what's the biggest that vector could be? What's the smallest that vector could be? Well, when we've got a circle, what we do is we draw in a secant. And that secant goes through the origin, because that's our starting point, the vector, and through the centre of the circle. And that will give us the biggest possible one and the smallest possible one. So basically you join the centre of the circle to whatever the starting point is. We know the distance to the centre, we can certainly work that one out, is going to be 2 root 2. We also know the radius is 2. Therefore the minimum one must be 2 root 2 minus 2, such as that little one down here. And the maximum one must be 2 root 2 plus 2, and there's the range of we could have. Strap yourself in for this one. Sketch the region of the complex plane defined by the real part of z is greater than or equal to the argument of z. And they're just reminding us, the argument of z, we're talking about the principal argument of our complex number. So the real part of z is greater than or equal to the argument z, and you might be thinking, oh, hang on, you wrote little a, not capital A, but in this case it's okay because I defined over here that the argument's going in between minus pi and pi. Well, if we're going to draw a region, we want to know what the boundary curve is. What on earth is that curve? I got no idea. So let's go back to Cartesian and see if I recognise it. The real part of z, well, I know that's just x. The argument of z, well, that's the inverse tan of the y over x. I still don't know what that is. So I'll find the tan of both sides. I'll make y the subject. It comes out a bit clearer. Aha! We're talking about the curve y equals x tan x. So that was the first challenge. You actually have to work out what on earth does the graph y equals x tan x look like. So over here I've drawn the two curves. Tan x, the one I've done in red there, and y equals x, and we're multiplying these two curves together. I know x is an odd function. I know tan x is an odd function. Therefore my new one must be an even function. Okay, I know we've got symmetry. Regions, let's work out where we are, and I'll just go, well, positive times positive is positive, and so on. All right, I know where the curve now exists. A bend towards asymptotes, all those sorts of things. It ends up looking like that. There's y equals x tan x. All right, I've worked out the boundary. Now I've got to test all the regions, but there's actually a few regions I need to check. Quadrant 1. Let's see what's happening over in quadrant 1. That would be where the argument is between 0 and pi on 2. I want to pick a point that's in that region that I can test. And I need to pick a point that I definitely know is in that region. I'm going to pick the point pi on 2, 1. And you might be saying, hang on, that's on the asymptote. Yeah. I didn't say I'm picking a point on the boundary curve. I said I'm picking a point in the region. And the one thing I know for sure is pi on 2 on 1 definitely isn't on the boundary curve because it's on the asymptote. So it's okay to pick that point to test the region. And let's have a look at it. Okay, I've picked the complex number pi on 2 plus I. The real part of that is pi on 2. Is pi on 2 bigger than the argument? The argument of that, well, hang on. What's the argument of pi on 2 plus I? Well, I don't really care because all I know is it's going to be something in between 0 and pi on 2. So yes, the real part has got to be bigger than whatever that argument is. So yes, that one's okay. I'm on that side. Quadrant 2. Pi on 2 is less than argument of z pi. Well, actually in this one, I don't really even need to pick a point because here the argument is always going to be a positive amount and the real part is always going to be a negative amount. There can't be any points in that region that'll satisfy it. So we're not there. Quadrant 3. Okay, let's pick a point. So this time I've just picked minus pi on 2 minus 1. So there's my point. The real part is negative pi on 2, but we know the argument has to be between minus pi on 2. So yeah, that is true. I'm in that section there. That just leaves me with the fourth quadrant. Again, I don't need to pick a point in the fourth quadrant because in this one, the real part is always positive, but the argument is always negative. So every single point in that region. So it looks like we've got our answer, but there's a few things to point out about the answer. Argument of 0 is of course undefined, so it does not satisfy that original equation. We wouldn't be able to substitute 0 into that and get an answer. So 0, 0, not part of the solution. Circle that. In fact, anything along the left-hand side can't be in the solution because at that point, or for all those points, the argument is defined to be positive pi. So how is the real part, which is negative, going to be bigger than positive pi? It can't. So we dot that. And the other thing to point out, it actually extends past pi because the domain of the function is not minus pi to pi. It was the argument that's in between minus pi and pi. Z wasn't in between minus pi and pi. So actually it just keeps extending all the way on the right hand side. Now there is our final picture. So let's just have some fun drawing pictures.